This presentation will show the progress made in the development of a pilot plant for fine dry coal beneficiation. The processing of fine coal is becoming increasingly important in countries worldwide, with millions of tons of fine coal being produced each year, either as a byproduct of general mining or through coal processing activities. Historically, these fines were discarded and placed on stockpiles. However, this is no longer the case. These previously stockpiled fines are now mainly being processed using wet beneficiation methods such as cyclones and spirals to extract their value and lower the environmental impact. The coal mining industry faces an obstacle when using these wet separation methods because they require large amounts of water. This makes these methods difficult to use in water-scarce regions, and this is one of the reasons why countries around the world are leaning towards dry beneficiation. Dry beneficiation is not a new concept and has been around for several decades, with air jigs and air-dense medium fluidized beds as some well-known dry beneficiation methods. For the past several years, a new development in dry beneficiation has been investigated. This method is known as winnowing. Winnowing has been used in the agricultural and pharmaceutical sectors for decades and works by separating the products from the discard using a stream of air. However, the method has not been successfully implemented in the mining sector, and there is very little data available on its applicability to fine coal. Several studies show that winnowing can be used to beneficiate -6 mm coal, and a study by the Northwest University that concluded in 2019 indicated that winnowing can work as a dry beneficiation method for fine coal. Building on the results from 2019, two prototypes were constructed to validate the winnowing method. These prototypes were tested and further optimized to improve their design before combining them in a single modular winnowing pilot plant. The size separation nozzle on the left works on the same principle as a vacuum cleaner. Particles are transported on a flat surface just below the nozzle inlet, and then depending on the air velocity moving through the nozzle, selected particle sizes are lifted up, while other sizes are left behind on the surface. The second prototype is the density separation chamber, shown on the right. The separation chamber works on the traditional principle of winnowing, except that the airstream used to separate the particles is generated by suction instead of the traditional blower. Particles that enter the separation chamber experience an external force from the air, and based on the individual density of each particle, it is displaced a certain distance through the length of the separation chamber. The design for the winnowing pilot plant was created by combining these two units. It has a single feed point that transfers the coal particles to the first stage, which is the size separation. Each nozzle then picks up a different size range of particles based on the preset air velocity and transfers those particles to stage 2, which is the density separation that occurs in the chambers at the bottom. The pilot plant was operated as a batch system, feeding 1 kilogram of -6 mm coal per run. Both the nozzle and the separation chamber were assessed individually to test their separation capability, and the results from the nozzle and the separation chamber will be discussed separately. After feeding the nozzles with a 1 kilogram sample of -6 mm coal and analyzing the data, the results show that there is very little size separation. However, as seen from the graph on the right, each nozzle does favor a different size range, which means that with further optimization, a better size separation would be possible. When analyzing the density of the particles lifted by each nozzle, it was found that even though the nozzles do not completely separate the particles by size, a density separation does occur, as shown in the table. This means that the nozzles could possibly be used as a separate dry beneficiation method in the future. When feeding the same 1 kilogram sample through the separation chamber and using a helium pycnometer to determine the average density of each of the 15 separation bins, the results indicated that a density separation can be achieved at relative densities as low as 1.5. As shown by the graph on the left, it would seem that a density separation is achievable without doing the initial size separation. Furthermore, when evaluating the content in each bin, it was found that most of the sample mass accumulated in bins 2 to 6, with very little material present in the outer bins. And although this is the case, the average density of these outer bins was still below the 1.5 average density mark. indicating that a density separation using the separation chamber is possible. Apart from the density separation, the size effect needed to be tested. To do this, a PSD was done on each individual bin. The PSD on the bins did reveal a size discrimination taking place during the separation, as shown in the figure on the left, with most of the larger particles reporting to the first 6 bins, while most of the small particles are collected in bins 8 to 15. The overlap between the particle size ranges, however, is still very big, and this does confirm that a two-stage separation is necessary, with the initial stage separating the particles by size, and then further separation takes place by density. This is further confirmed by the decrease in the average particle size as the bin number increases. This is shown by the figure on the right. Overall, the separation data is very promising, with relatively high yields being achieved at low bin densities. Bins 2 to 15 are all below the average bin density, and thus, if the desired product density is set to be at 1.5, the yield would be around 95% for this specific high quality coal. The bin densities and size analysis do show that the equipment is capable of separating fine coal to a certain extent. However, further investigation and testing will be needed to optimize the process, as shown by the partition curves on the right. The partition curves were set up by combining several bins to create a product and a discard. For each combination, a partition curve was constructed, and as seen from the curves, the separation is adequate but not yet very efficient, and thus further investigation and testing is needed to optimize the density separation unit. The results from the study were unexpected but promising, and although the pilot plant did not perform as expected, the results did indicate that both of the pieces of equipment that were designed are capable of separating -6 mm coal. The results also opened the possibility of using the separation nozzle and separation chamber as two separate dry beneficiation processes, or combining them in a different manner to achieve an even, cleaner product. In general, the study was a success, proving that the size separation nozzle can separate particles by size and density. The separation chamber can beneficiate dry, fine coal with a very low density while maintaining a high product yield, and that the winnowing as a dry beneficiation method for fine coal is showing great promise. Future work on the winnowing method will include the following: the effect of particle shape on the separation, converting the batch system to a continuous system to increase the throughput, increase the size range to test the separation limits of the winnowing chamber, and testing the method on different types of coal to see the separation capability of the method. We would like to thank everyone involved in this project for their contributions. Without your help, this would not have been possible. Thank you very much.